So today's notes are going to be on trapezoids and kites, which is our section 8.5 content. So we're now moving away from parallelograms. We know that a parallelogram is a quadrilateral where the opposite sides are parallel, and then we have all those other properties that occur from that. We get opposite sides congruent, opposite angles congruent, consecutive angles supplementary, diagonals bisecting each other. And then we looked at specific parallelograms in section 8.4, which was rectangles. Specific to that was four right angles, rhombuses, which were giving us four congruent sides, and then squares would be four congruent sides and four right angles. And then we had diagonals being perpendicular inside of a rhombus and diagonals being perpendicular inside a square. We had diagonals being congruent in a rectangle and diagonals being congruent in a square, right? So that was everything that we covered so far in this chapter. So now we're going to kind of move away from parallelograms because there are other quadrilaterals that do not fall underneath the parallelogram category, and those would be the trapezoids and the kites. So what is a trapezoid? A trapezoid is a quadrilateral with exactly one pair of parallel sides. So a parallelogram had two pairs. A trapezoid now only has one pair of parallel sides. And we call those parallel sides the base. So a trapezoid is going to have two bases. And then the non-parallel sides we're going to call legs. So if you hear me talking about base, that means those are the sides that would be parallel on the trapezoid. If you hear me saying the word leg, then that would be the non-parallel sides. Okay? All right. So if we had an isosceles trapezoid, well, that's when our legs would be congruent to each other. So an isosceles trapezoid is when the legs of a trapezoid are congruent. That makes it isosceles, right? If we think back to when we had an isosceles triangle, get rid of this for a second. An isosceles triangle, we had congruent legs. And because we had congruent legs, we had congruent base angles. Well, now if I chop off the top of that triangle and turn it into a trapezoid, now we have two bases, which means we're going to end up with two sets of base angles happening here. Okay, so let's go ahead and get those into our theorems. So in theorem 8.14, again, you don't need to have these numbers memorized. It's just the 14th theorem in chapter 8. If a trapezoid is isosceles, then each pair of base angles is congruent. So if we know that it's isosceles and we know that those legs are congruent, then I know that each of those base angles are going to be congruent. So the top base angles will be the same and the bottom base angles will be the same. We also know, since we do have one set of parallel sides, I've got a consecutive interior angles here, and I've got consecutive interior angles here. We know that if lines are parallel, then consecutive interior angles will be supplementary. So I know I still have some supplementary angles there. It's just that, unlike in a parallelogram, these will not be supplementary to each other. Neither will these. But they will be congruent if it's isosceles. And then we have the converse. If a trapezoid has a pair of congruent base angles, then we know that it's an isosceles trapezoid. So if I'm given the base angles being shown congruent, then it's safe to assume that the legs will also be congruent. So this is just the converse of the last one. The last one was giving us congruent legs, which then gave us congruent angles. Here we're giving congruent angles, which would then get us congruent legs. All right, next theorem, if a trapezoid is isosceles, if and only if its diagonals are congruent. They are not bisecting each other. You can clearly see that this is not the same length as this, right? One's shorter than the other. So they're not bisecting each other, but your diagonals will be congruent to each other if the trapezoid is isosceles. So the red and the orange added together will equal the other set of red and orange. Right? So you would see something like, if this whole thing is 5, then what's this whole thing? Well, it would also be 5. Okay, so your diagonals will be congruent. All right, so let's do some work. Given the following isosceles trapezoid, find the measure of K. So because it's isosceles, I know that this set of base angles will be the same, and I know that this set of base angles will be the same. So the measure of angle K will also equal 85 degrees. The measure of angle M, well, how can we find that? Well, M is down at the other base, but I do know that these will be supplementary because that's my one of two sets of consecutive interior angles. So to find M, we're going to do 180 minus 85. So what would that put us at? 95 degrees? And then M and J are the same, so that makes the measure of angle J also equal to 95 degrees. All right, mid-segment. I'm going to pause here for a second. So let's go back to chapter 5 when we were talking about doing mid-segments. You guys did a bunch of these. You did artwork on triangular mid-segments. When we had a triangular mid-segment, it was the line that connects the midpoints of two sides. We knew that that line was going to be parallel to the third side. And there was also a theorem that we had. If this was 10, we knew that that mid-segment was half that length, so it would be 5. Well, again, if I chop the top off of this triangle, oops, I should have picked easier numbers. Let's go 6 and 10. That'll be easier to, nope, that won't work. 6 and 12. It's easier to find the middle of that. If I take off the top and make a trapezoid and create a new mid-segment, any guesses on what the length of that mid-segment would be? Well, if you're trying to think of what is exactly in between 6 and 12, well, 9 is exactly in between 6 and 12, right? Because how do I go from a 6 to a 12? I add 6. What's half of 6? 3. So add 3, puts 9 at the middle. Or take 6 plus 12 and cut it in half. That would get you to 9 also. Okay, so that's where we get the mid-segment theorem of a trapezoid. So the definition of a mid-segment of a trapezoid is the segment that connects the midpoint of the legs. And when we create a mid-segment of a trapezoid, we get the mid-segment theorem, which the mid-segment theorem says the mid-segment of a trapezoid is parallel to each base and its length is 1/2 the sum of the lengths of the bases. Okay, so if this was, let's say that's base 1 and that's base 2, our mid-segment would be equal to, space, I'll go down here, your base 1, add it to your base 2, divide it by 2. So like in that example, I had 6 and 12. So 6 plus 12 is 18, divided by 2 is 9. So the mid-segment's length was 9. All right, so let's put into practice. Here my bases are 12 and 28. Find the length of the mid-segment. So the length of MN is going to be equal to 12 plus 28 cut in half. Well, 12 plus 28 is 40. Cutting that in half tells me that the length of M to N is going to be 20. All right, let's do it this way. Here I have a mid-segment length and one of the bases, so now I got to find the other one. So we could either use some algebra. We know that the mid-segment, which in this case is 8, is equal to the two bases added together, cut in half. How do we get rid of a divide by 2? Multiply by 2 on both sides. So that gets you 16 is equal to 5 plus x. Subtracting 5 gets you 11 is equal to x. So that means my base has to be 11. Or you could just use some mental math here. How do I go from a 5 to an 8? Well, I add 3. So for it to be consistent, I just need to add another 3, which would get you to your 11. Either of those methods work. You choose. The first method, the algebraic method, will work out nicely when we have algebraic expressions involved, like we do here. So now I can't just think add 3, because I don't know what the top or the bottom need to be. So here we have to use some algebra. So again, remember your mid-segment, which in this case is 20, is equal to your 2 bases added together. So one of my bases is 2x minus 8. The other base is 5x minus 15, and then we're going to cut that in half. All right, so let's simplify by combining like terms. I get 7x minus 23 divided by 2 is equal to 20. If that 7x and that 23 were even numbers, I would just divide those by 2 and cut it in half. That would be nice. But since 7x and 23 are both odd, I probably don't want to deal with fractions or decimals. So let's get rid of that divide by 2 by multiplying by 2. What I do to one side, I must do to the other. So now we get 40 is equal to 7x minus 23. 40 plus 20 is, or 40 plus 23 is 63 is equal to 7x. Divide by 7 gets us our x is equal to 9. There's your answer. Okay, so that gets us through everything you need to know for trapezoids. So now let's move to a kite. And yeah, a kite is pretty much the basic shape of the kite that you fly in the sky, or at least how it started. Now they have kites that are pretty elaborate and fancy. So a trapezoid has only one set of parallel sides. A parallelogram has 2 sets of parallel sides. A kite has none. You've got nothing parallel happening here, so you're not going to have any consecutive interior angles that would be supplementary. We still do know that all 4 angles should add up to 360 because it's a quadrilateral, but we don't have anything parallel. So a kite is a quadrilateral that has 2 pairs of consecutive congruent sides. So a quadrilateral that has 2 pairs of consecutive congruent sides, and you can see them pretty obvious here. So here you have this long side congruent to this long side, and then you would have these 2 short sides congruent to each other. That would be your kite. All right, so now we got all sorts of things happening inside of a kite when we throw in the diagonals. So if a quadrilateral is a kite, then its diagonals will be perpendicular, and we're okay dealing with those perpendicular diagonals because we've got practice with it with our rhombuses and squares, dealing with our special right triangles, which are our 45, 45, 90, and our 30, 60, 90. If we don't have special right triangles, then we do have to use trigonometry, which is our sine, cosine, and tangent, and that's okay. Or maybe just the Pythagorean Theorem, a squared plus b squared equals c squared could work here. Okay, so if we have a kite, we know that our diagonals will be perpendicular. If a quadrilateral is a kite, then exactly 1 pair of opposite angles will be congruent. And notice where those opposite angles are located. They are located in between the non-congruent sides. So it's happening in between the non-congruent sides. The angles occurring at the congruent sides, so here and over here, those won't be the same. So those won't be congruent. The only ones that will be congruent are those tops and those bottoms. We also have some other interesting things happening with kites, and I don't think they have, oh yeah, I do have them in there. Okay, never mind. So let's move on to example 3 using one of those 2 theorems that we just discussed. Find the measure of angle D in the kite shown. So D is one of those angles that's in between the non-congruent sides. So D and F would have to be the same. So if we wanted to do it algebraically, when we don't know something, we make it a variable. In this case, we can make it x. And I know that all 4 of those angles should add up to 360 degrees. So now I have 2x plus 204 is equal to 360. 360 minus 204 is, oh my goodness, it's late in the game. What is that? I can't even type it into my calculator correctly. It's 156. Whew. Is equal to 156. Dividing that by 2 gets us x to be 78. Or you could have just started doing 360 minus 80 minus 124 and then get that answer and then divide everything by 2, right? Because we know that both of those have to be the same. All right. Other theorems about kites. If a quadrilateral is a kite, then it has one diagonal that bisects a pair of opposite angles. So now we had congruent angles happening on the non-congruent side intersections. On those angles that are not the same, we do have something happening there. We have the diagonal bisecting those angles. So those angles are getting cut in half. That will not happen on the congruent angles. They will not be cut in half. Okay, so if we look here, so let's find the following angles. The measure of angle E. So my congruent angles are occurring here and here, which means that angle E and angle I would be the ones that are being bisected. So if E's top half is 40, then the bottom half is 40, so altogether it would be 80 degrees. Angle KSE is this angle right here, which since it's perpendicular, that's going to be 90 degrees. So if this is 90 degrees, how can I find that angle right there? Well, I have a 90 and I have 40, so that tells me that part of the triangle's got to be 50 to add up to 180. So all of K would be 50 plus 65, so 115 degrees. Okay. And then, not that it was asking, but if that's 40, then we know that this would also be 50. And since T and K are congruent, this would be 65. And then we know if this is 90, 90 minus 65 would tell me that these two angles would have to be 25. Right? So you can find all those unknown angles in there if you needed to. Alrighty. Example 5, let's solve for x. So we have 90 degrees happening here. I have 90 degrees happening here. I'm assuming that 8x degree is right there. Because this is a non-congruent angle, if the right side is 5x, the left side would also be 5x minus 1. So now I have a right triangle where I know all 3 of my angles. And we know all of them should add up to 180. So I could do 90 plus 8x plus 5x minus 1 and set that equal to 180. Combining like terms gets us 13x plus 89 is equal to 180. 180 minus 89 is 91. Dividing by 13 gets us x to be 7. All right. Another theorem for kites. If a quadrilateral is a kite, then it has one diagonal that bisects the other diagonal. So only one of the diagonals will be cut in half. Usually it's the shorter one, but it's going to be the diagonal that's connecting the two congruent angles. So A and C are congruent here. So if you kind of think about folding it on diagonal BD, it should lie on top of each other. So that would mean this length would be the same as this length. You can clearly see this length is not the same as that length down there. One is definitely longer than the other. All right, so let's use that theorem. Solve for x here. So I have the diagonal connecting the non-congruent will bisect the diagonal connecting the congruents. So 2x minus 7 should equal 15. 7 plus 15 is 22, so x will be 11. Sorry, I feel like my handwriting is getting worse as I go. All right, and then example 7. Let's do some work to find unknown sides. So we've got a right triangle. I need to find the length of y. So I'm going to focus on this right triangle right here. So if I ignored all the rest, which I can erase it because I can, go back to chapter 7. Oops, I don't want to get rid of the 8 though. Bring that back. Going back to chapter 7, we could just do some good old Pythagorean Theorem. So a squared plus b squared equals c squared. 64 plus 9 is equal to y squared. 64 plus 9 is 73 is equal to y squared. Square root, square root. Can I get anything out of that? Perfect square wise? I don't think so. So I think that's just going to stay the square root of 73. So that stays the square root of 73. So there's my y. Now let's bring x back. X is over here, so let's get rid of all of the stuff that we don't need with x. So I'll get rid of that. Oops, I do need this. Bring this 3 back. If that's 3, then I know that this down here is 3. That's the only reason why I need that. And then I'll get rid of all of this. So there's this right triangle, where x is the hypotenuse again. So 4 squared plus 3 squared equals x squared. 16 plus 9 is 25 is equal to x squared. So x is equal to 5. Okay, so Pythagorean Theorem works nicely there. If I was given any of the angles, then I would probably have to use trig to solve for the outsides of the kite. That ends your notes.